All right, so thanks everyone for coming. We're very happy to have Michal give us the first talk of the seminar on extensions of globally valued fields and applications to arithmetic geometry.
Yes, thanks for having me here. And okay, I thought I'll start with my talk with various cases of fields with some extra structure and how model theoretic analysis looked like in these cases, because this is a process that I want to do for global fields. So I thought I'll just briefly start with this history of fields with extra structure from the model theoretic point of view. So, okay, so here just on the left, we have just fields. So yeah, okay, so maybe first they were talked about, Dedekind talked about them, so this is where Kuiper appeared. And then if we talk about this class of structures, fields, there are ones that are special, the algebraically closed fields. So in model theory, they have some property within this class that is called existentially closed. So instead of defining this property, I want to go through these examples and somehow tell you that each of the classes of fields with an extra structure has some special class, and maybe then to compare any field with the special class fields, we can do some kind of Galois theory, or we look at the automorphism. But then if we understand extensions of fields and these special fields, it's better to do geometry there. So this is roughly the slogan that I want to do here. So okay, so I guess yeah, you could start with Gauss. Apparently Steinitz in 1910 was the first one to show that every field has an algebraic closure and to do it formally as we do it today. And of course you can do algebraic geometry there. We have Null-Stellensatz, which I'll come back to later. Yeah, Hilbert proved it. And we also have some spaces which have Zariski topology. And this is the context we talked about fields usually. Then another model theoretic structures that one can consider, or just mathematical structures, are fields with a derivation. So fields with a additive homomorphism that satisfies this Leibniz rule. And okay, to be honest, I couldn't find who talked about them first. But I know that in this case, there is an analog of being algebraically closed. It's called being differentiably closed. So it can also be defined in terms of having solutions to some simple class of one variable equations, like algebraically closed fields usually are. And there is also differential Null-Stellensatz. And these differentiably closed fields are also exactly the ones that satisfy the differential Null-Stellensatz. So the differential algebra with derivatives. It was developed by Reed in 50s, and then his student Kolchin, and there is Kolchin topology for differential varieties, where instead of Zariski closed sets, one looks at sets defined by differential equations. So here, this also has some geometry that has its spirit, or yeah, it's a bit different.
So when differential algebraic geometry started being developed, there was still no notion of a differentially closed field.
So
I just noticed that date is earlier than that one, is all I'm saying.
So I guess yeah. So Reed proved Null-Stellensatz, but okay, but maybe to recognize this class, this was Robinson. Yeah. Okay. Then we can have another thing that I thought I'll mention because it's relevant to this year's program, fields with an order. So Hilbert, Hölder, Hahn, many people started talking about these structures, and of course they were there way before. And here, the existentially closed ones will be actually the real closed fields, for example, the real numbers, and they are characterized by the fact that their Galois group is just Z2. So they have a unique degree 2 extension by a square root of -1 that is algebraically closed. And this is, well, this characterization is essentially Artin-Schreier theory in 1965. But Tarski was the one who studied the theory of the reals, and he understood existentially closed ones in 50s. And then here we have real algebraic geometry, algebraic equations, and inequalities. And okay, maybe just as an advertisement, we also have this world of ominimality, which, as far as I know, was initially the first paper of ominimality. The one that coined the definition was by Pillai Steinhorn in 1986. So okay, we see that the dates are later and later. We also have fields with an automorphism. So there is a theory that it's not possible to describe it that easily, but I can say that, for example, a generic automorphism of algebraic numbers is existentially closed. So it satisfies some form of Nurstein-Satz with difference equations, and the algebra of those was developed by Kohn, and there is also some kind of geometry that one can do here. So there is a notion of difference schemes, and so on and so on. And then, okay, so now maybe I'm getting closer and closer to what I'm actually going to talk about, but this is the local picture, the valued fields considered by Hensel, Krull. So we have the axioms of evaluation on a field valued in maybe real numbers or some ordered abelian group. And then in this case, actually, the existentially closed ones are just the ones that are non-trivially valued and algebraically closed. So there's no extra condition on this extra structure that valuation is. And here the relevant geometry. So, okay, I could write evaluative spectra, Berkovich geometry. So, okay, maybe here before I was considering sort of discrete structures, and here there are actually two pictures that should be here, where one is abstract valuations valued in ordered abelian groups, and another one is actually real valuations, complete real valuations. So this would be Berkovich geometry. Yeah, so here are the two pictures. I mean, here really there are two kind of existentially closed structures. One, these ones are in continuous logic, so real numbers, and these ones are in discrete logic, so any ordered abelian group. Yeah, okay, so this is Berkovich. Yeah, and actually, when I was preparing this, I sort of had a lot of fun because I thought I'd just look up how many of these people were here at some point of their lives, and it was almost everyone. I mean, okay, maybe not Gauss, but so yeah, so I even have some dates, but maybe I can say it later. So then this is the classical picture, but now the structures that I want to consider are global fields. So this is like a global version of fields. And then I want to consider some generalizations of global fields. So one of the generalizations would be these globally valued fields. And this is a notion related to Gubler's M fields or adelic curves by Chan and Morivaki. So they were introduced by Hrushevsky and Benyakov, and so there is a class of structure which somehow behaves like the top part of this table in these cases. And the main question I want to talk about today is these existentially closed ones out of global fields, what they should be. We know some examples, but we don't have such a good understanding of what they should be. And yeah, I also, one of the questions I wanted to also ask here is what should be the geometry here? I mean, there are various geometries that people do over global fields, like Arakelov geometry. There are also some geometries over these new exotic objects, let's say. There is some Arakelov geometry in families, like recent Yuan Zhang, adelic line bundles on quasi-projective varieties. So there are some candidates of geometry that one can do here, but yeah, this is really the main place where this talk will be happening. Okay. So okay, but so actually, what do I mean by this geometry or these global fields here? So yeah, maybe this was like a sort of an introduction where I want to compare what kind of process I want to do to some structures to understand some kind of equations, but what kind of equations, what is the problem that, or types of problems that I really want to consider. So let's say we are given equations where we have some polynomials, we want to find their solutions. So we have some part of equations like in algebraic geometry, but then we also have conditions bounding the complexity of solutions. So maybe we want the height of the first element to be between some two elements, two real numbers. Maybe we want the height of some polynomial applied to all the elements to be bounded by some other numbers, so on and so on. And so maybe we have some number of conditions, and we want to solve these kind of problems. So really, okay, height is some notion of complexity. So usually, or maybe on rational numbers, the height of the number a divided by b is log max absolute value of a and absolute value of b. If a, b don't have common divisors, and there is a natural extension to the algebraic numbers of the height. So, oh, actually, will people see here? Yeah. So in this case, the height of an algebraic number alpha is just 1 divided, can be given by this formula. For example, we integrate over the circle the minimal polynomial of alpha with integer coefficients and GCD1 coefficients. Okay, so this is the height that we can consider in these equations. One could ask about this problem. Let me also say that also there is a natural extension of heights tuples. And then, okay, I'll use a different formula. So if we have some algebraic numbers alpha 0 to alpha n, then I can define this to be 1 over the degree of a field which contains all of these elements times the sum over places of k of log max absolute value of alpha I times some weights, and these weights satisfy product formula, so that if I just take one alpha, this is always 0, and that's why this only depends on the vector that this tuple generates in the n plus 1 dimensional space. So just to hint why one could consider such problems, for example, Ziegler's lemma can be seen as a problem of this sort. If we have linear equations and we want to bound the height of solutions of linear equations. This is a fundamental lemma that one can use. Okay, but Ziegel's lemma is about linear equations, and we could ask about general equations. So general equations are quite complicated. And if this question is in this generality, the problems are that, for example, in rational numbers, the answer to even the first part is expected to be undecidable. And in fact, with height conditions, with height equalities, it is by a recent work of Garcia, Fritz, Pasten, and Vidal. So if we want to understand this problem, we cannot work in rational numbers because even just the geometry there is difficult. Okay.
So I guess question, sure. If you're in Q or global field, the height being less than something just means that you're one of finitely many things, right?
Yes. Yeah.
If you're looking for solutions, how does the height help in making things undecidable and decidable?
Well, okay, so it depends what kind of questions you are, what kind of question you ask. Like if you, for example, bound the heights of all the coordinates, you just have finitely many. So in that case, you have an algorithm to find them. You just can test all of them. Yeah, okay, but I'm just saying that in rational number, if you have no conditions here,
okay.
Yeah, so you have maybe some also inequalities conditions, and if you don't have them, then the first part is already expected to be undecidable, but it's not known. Yeah, if you have integers, it's known to be undecidable. This is Michal Szachniewicz. Okay. So then, okay, so what we do if we cannot solve equations in some places, we just extend the domain. So we could ask in algebraic numbers, and of course in algebraic numbers, the first part is just Nullstellensatz. So equations are possible to choose if and only if the ideal they generate does not contain one. However, the second part may be problematic. So I want to write in Q bar, there are obstructions. So let me write some obstructions, some properties of these heights that obstruct whether a solution can be obtained. Okay, so these would be very simple obstructions. So, for example, if one of the equation is that x1 times x2 is 1, and we have height of x1 times x2, dot x1 times x2, then this has to be 0. Okay, so these are obstructions, but more like properties of the height. Also, this height is invariant under permutations. This is clearly from this formula. Also, if I have a height, if I have some two projective tuples, and I form a projective tuple by taking all possible products to this Segre, then this is the sum of heights. Again, this follows from this formula. And these are very simple obstructions. Also, the more tuples I have, the bigger the complexity will be. And I have triangle inequality. If I have two tuples, I choose some vectors such that this is non-zero, then this will be smaller or equal than the height of x, y, plus log 2. Okay, so I wrote some things that, for example, if the equations, if we have y equals x squared, then from this it follows that the height of y has to be 2 times height x. So these are some obvious obstructions for existence of a solutions to such equations. But in fact, these are all the obstructions. yeah, okay, so here I mean, like, if, for example, we wanted the height of y to be smaller than 1 and the height of x bigger than 1/2, then we cannot do this. Okay? Okay, so what do I mean? That these abstractions are in fact all the abstractions. So in fact, one can prove, this from my 2003 paper, 23 paper, that assume there is no proof of contradiction using equalities, inequalities, and abstractions. Then equalities and inequalities can be solved in Q bar. Okay, so this is maybe a slightly non-standard way of stating a theorem about existence of a solution. Let me give you equivalent way. Yeah, okay, so to do it in an equivalent way, we need one definition. So say a global height on a field K is a tuple, a sequence of functions that take projective tuples in K and map them to non-negative real numbers that satisfying abstractions, satisfying these axioms. So let's say we are given a field and we define this as some kind of structure that the field can possess or not. So then what this theorem says, okay, and a field with a global height, this is what a globally valued field is, explaining maybe the type of the talk. So then this theorem equivalently can be stated the following way, more standard way. So assume that equalities and inequalities have a solution in a globally valued field. In, okay, extending Q, then they have a solution in Q bar. And this is really the definition of being existentially closed in logic. If we have some class of structures satisfying some axioms, and we consider them in some language, so we're talking about equations of some form, the structure is existentially closed exactly whenever you can solve the equations in some extensions, then you could have solved it already in the original structure. So algebraically closed, they are existentially closed because they satisfy Nash-Spell ansatz, because a non-empty variety has a point already in an algebraically closed field. And what this theorem says is that the algebraic numbers with this global height, with this height structure, are an existentially closed model of this theory.
Sorry, I'm a bit lost. So here in your definition, you assume that K has an absolute value plus a global height.
No, it has only, so K is some field.
Yes.
Together, and K as a structure, it's a field, and for every n.
I understand, but what you call a globally valued field is what?
Okay, okay, so globally valued field. So this would be a field together with a global height on it.
Just a global height.
Yes.
Right.
Okay. Yes.
You
So-
have a concrete characterization of these exponentially close things along the lines of solving monic polynomials?
So this is well, I don't, but I want to have. And the rest of the talk, I'll try to explain what I know about them and what I would like to know. And so I'll ask more questions. But yeah, this is exactly what I would like to understand: how to describe the class of existentially closed globally valid fields better. Yeah. So okay. But coming from this, it seems that okay, whenever we have such some polynomial equations with height problems, then to solve them in algebraic numbers, it's equivalent to solving them in some extension. So naturally, the question arises how to describe extensions of Q in terms these globally valid field extensions. Okay, so it's long. The abbreviation is GVF. Okay, how to describe these extensions? So okay, one can do this with heights, but I can also do this in a few equivalent ways. So let me give you a theorem from a joint work with Itai Ben-Yakov, Pablo Destik, Undi Hruszowski, and me from 24. So let K be a countable field. So countable is really so that I can say less when explaining the statement, but it's not really a problem. Then a GVF structure on A is equivalent to, and I explain what I mean by equivalent. So first, an equivalence class of a valuation valued in a Banach L1 lattice. What does it mean? So this is a function that goes from non-zero elements of the field to L1 of some measure space that satisfies the axioms of the valuation. So V of xy is V of x plus V of y. We also have triangle inequality, but here we upgrade it so that it also includes Archimedean places. So we have minimum of V of x, V of y, plus minimum of V of 2 and 0. So okay, so first when one learns about valuations, the values are real numbers, then they can be in any ordered abelian group. But here, why not be in a Banach lattice? So you can define minimum here, you can add, so you can write these axioms. And the most important one is that, well, this always has an integral operator where it's just integrating the function in this space. And you want this to be 0 for all x in k times. So this is like a product formula. This is one way of describing a GVF. And then in heights, from height of A0 up to AN, they can be defined by integral of minus minimum of V of AI. So this minus minimum is a function, and one can take the integral operator, and this one can show that these axioms imply that they will satisfy this list. Okay. So sometimes people ask why minus, but this is because minus minimum of minus logarithms is log max. So okay. And then another thing, and this is maybe something that feels more global, is that to equip a field with a structure like this, it's equivalent to equipping it with a measure mu on the space of absolute values on K. So this is the set of functions from K to real numbers that are multiplicative this time, and they satisfy a triangle inequality. Yeah, so the multiplicative version of evaluation. And then these are real valid functions, so we have some natural topology there, or Borel sets and so on. It's a measure such that for all A in K, again, we have the product formula. So the integral of minus or just logarithm of absolute value of V, where the evaluation, where the norm varies. So here I denote norm V and V interchangeably. So this integral has to be 0 for all A in K. And furthermore, these functions must be L1. So the integrals are 0, and these are integrable functions with the absolute value. And then from here to pass to 1, one takes a function B from K to L1 of MK with this measure me, just the evaluation function. So A is mapped to a function that maps V to minus log A. So this is maybe a bit tautological, but what is non-trivial with the statement is that actually whenever I have heights that satisfy these axioms on any field, then there will be a measure that satisfies the product formula, and this measure will be essentially unique. So it won't be unique because of some stupid reasons. So you can have p-adic absolute value there, but you can also have the square of p-adic absolute value there. And if you take the logarithm, like you may take Dirac delta at one of them, or 1/2 Dirac delta at the other, and it behaves the same. But up to the scaling, this is everything that can happen. Okay, yeah. So just summarizing, we started with some height equations that we wanted to solve. We know that to solve them in algebraic numbers, it's equivalent to maybe construct extensions of some kind where they are solvable. So we want to understand these extensions. This is a theorem that gives some way of understanding them. But okay, I mean, to construct measures on spaces of absolute values, it can be complicated. So there is, in fact, another way of looking at them through Arakelov geometry.
What are the equivalence relations of height functions? I mean, you say that a height function is equivalent to such data, but is there, I mean,
no, so here's
height which is equivalent to such a datum, or a correct class of equivalence heights?
So here the equivalence, so it's really height. So for every height, there exists, for example, the first point here says that for any height, there exists a unique up to equivalence, where equivalence is defined exactly as equivalence of valuations. Yeah? Banach L1 lattice. Maybe you also, if you want a unique, you should also assume that the tropical things that you can do, so like min and plus things that you do after image are dense, because you can also increase this size. Okay, but no, actually the up to equivalence is fine. Yeah, so up to equivalence for any height, there exists a unique valuation up to equivalence that satisfies this formula. Yeah, and this measure is unique up to some renormalization relation. Yeah, okay. So now another way to understand these structures is through Arakelov geometry. Okay, so why is that? So let's try to understand some extension. So take X over Q, a variety, and consider a GVF extension on the function field, the field extending Q. So this means that whenever I have a tuple of elements here, then I can measure its height. And if the tuple comes from rational numbers, it extends just the value logarithmic height.
So over here you have a condition on the Galois conjugates. How does the measure?
Oh no, so this is just the permutation.
Permutation.
Okay, I see.
So like, yeah, this is like, if I, instead of x1, x2, write x2, x1. Yeah. The Galois question is also a good question, but maybe I'll get to that later. Okay, so let's try to understand what is such an extension. So then, given a tuple of functions here, at a tuple of functions, it's like a rational function from X to a projective space. Or if it's F, we get a number, and this number is the height of the tuple represented by this rational function. If someone gives us a GVF extension, so the heights on the bigger field, we can build from rational functions on our variety, we can get some numbers, some numerical invariants. Okay, so we get some map. We can look at the set of all maps from here to PNs, where n vary and f vary. And we get a map from this set to real numbers. Okay, but then projective spaces, if you have two maps to projective spaces, if we later do Segre embedding on them, these obstructions axioms give us some rules. So in fact, this set is a monoid. You can add such rational maps by composing with Segre, because maybe if you like, the disjoint union of all PNs is like a group scheme with Segre. So this actually gives you a map from the Grothendieck group of this monoid. Okay, you also have to, if you want the things to commute, you have to divide by the symmetric group. But fortunately you have, because it doesn't depend on the coordinates. So you look at the classes of rational functions up to permuting the coordinates with the Segre, where I have two maps, I can map them in the product of projective spaces embedded in different. I take the Grothendieck group of that, and I map it into the reals. And this is a homomorphism. So this GVF extension is a homomorphism like this. Okay, but if you run algebraic geometry, you see this, and what is this? So these are like virtual maps into PN. So these are essentially line bundles. But when you look at line bundles on your variety, you don't remember the sections. The automorphism group, well, if the group of sections is 5-dimensional, you have some action of GL5. But here we only want the symmetric group to be the group of automorphisms. And so that's why this will turn out to be Arakelov B line bundles. So this is some rigidified version of line bundles on X. And so let me give a proper definition now. So let X be a projective scheme over Z whose generic part is X. So we lift equations to integers. So then a Hermitian line bundle on curly X is a line bundle on this curly object together with a Hermitian metric on the corresponding analytic line bundle on the corresponding complex manifold defined by the equation. So this is a Hermitian line bundle. And then in the node by P in the X, the completion of the group of Hermitian line bundles. So okay, so we have to complete to include some a bit maybe not smooth but continuous metrics, and then one can describe these structures on this extension in the following way. A GVF structure on U of X is equivalent. So really there is a homeomorphism between what I'm going to say and basis of all functions satisfying this to a positive homomorphism from the space of Arakelov B divisors. So I take the injective limit of all lifts of equations of X to integers, but even birationally. So X, the generic fiber of X is supposed to be birational to X, or I could say the function field of this scheme is just my fixed field. And it's a positive homomorphism from this thing to real numbers, and it's positive in the sense that here this has a natural cone, the cone of arithmetically effective line bundles. So these are line bundles that have a section that the norm, the Hermitian norm of the section is smaller or equal 1 everywhere. So here there are these arithmetically effective sections, and they have to go to something bigger or equal 0. And there is some normalization condition. But the normalization condition is not really a problem. So, okay, so because the point is that now the question is, how do I ensure that the GVF structure here extends the veil heights on rational numbers? But in fact, on rational numbers, there's only one such structure up to scaling. So the axioms I wrote here that I just erased, they're homogeneous, maybe up to like the part log 2, but it was an inequality. So if I multiply a height by 7, I still get heights that satisfy the axioms, maybe with 7 times log 2 instead. So okay, so on Q, in fact, there's only one. Yeah. And on all number fields and on algebraic closure of Q, there's a unique structure like this. So maybe up to scaling. So maybe this indicates some kind of naturality. And maybe let me mention that whatever left-hand side is a group lattice if one takes divisors instead. Yeah, so I mean, okay. If you like line bundles, you have line bundles, but if you prefer divisors, then if you take the limit of divisors here, you take green functions instead of Hermitian metrics for divisors, then this, in fact, this is a group, divisors you can add, I mean, this is how they are defined, but this is also a lattice because you take this injective limit and the minimum operation of divisors in the blow-up, in the limit over blow-ups, is just the intersection that you wait to get to a model where this intersection becomes a divisor. So this is, so really the space of GVF structures on this thing is some kind of dual cone to a cone of effective things. Yeah, okay. So, okay. And so let me say that this group lattice in some roughly equivalent language was already considered quite recently. Actually, it appeared in a paper by Ru Wojta and also by, yeah, so Wojta, he considered this kind of Arakelov divisors. Okay. Okay, so now you have various equivalent ways of looking at these new introduced structures. So there is a way of looking through Banach lattices, measures on spaces of absolute values, and there is this Arakelov way, which is supposed to be simpler, but maybe doesn't look like, depending on what you like. And so it gives some information because people have a lot of theory about Hermitian line bundles. So let me say that in nature, such positive functionals, positive homomorphisms appear to come from Arakelov intersection product. So this is a multilinear product on the dimension of variety over Z plus 1 two real numbers. So in particular, if I have an ample Hermitian line bundle on a scheme over Z, whose Chern form is strictly positive, then I can multiply elements from here by the codimension 1 power, and then this gives such a positive homomorphism. And in fact, things that come from this form are dense. So, okay, here maybe just, I won't explain it, but let me write a slogan that this, if someone gives me such a homomorphism and I'm looking for a line bundle such that product with this line bundle will be similar, this is sort of like some global Monge-Ampère equation. Okay. But overall places, not only the complex one. And this Arakelov intersection product, if we have some concrete data, it can be described in terms of, in simpler terms. So for example, if we have some variety that we're starting with, and we have maybe we have D plus 1 embeddings of this variety to different projective spaces, then the product of pullbacks of some natural matrix of O of 1 is roughly the height of the multi-resultant. Corresponding to this family of embeddings. Okay, so resultants shown. And now I wanted to delve deeper into this question of existentially closed structures like this and what is known about them. So of course, existentially closed structures like this, they have to Okay, so maybe it's not, of course, but one can show that existentially closed structures have to be algebraically closed, because in fact, any GVF has a Galois symmetric extension to its algebraic closure. So in general, this extension does not have to be unique, but there's a unique Galois symmetric one. There is some canonical Galois symmetric extension, but in general, there may be some non-Galois symmetric. And so it follows that these existentially closed GVFs are algebraically closed. But what else do they satisfy? So let me give you an example theorem, and then I'll ask some questions, and yeah, maybe I'll start talking about some things that I would like to know, and that maybe someone will know. So this is a theorem by Bediakov and Ruszowski in this generality, and Hancock and Blair over Q bar. So this was in 2009. And yeah, this is in some notes. Okay, but this maybe is not so. Okay, so the theorem is the following. Let V gamma, so this is L1 of something, V an existentially closed GVF. We assume we start with an existentially closed GVF. Then, for every epsilon bigger than 0, and F in gamma with integral of F being 0, there is A in K such that the integral of V of A, so V of A is some function in some space, minus F is smaller than epsilon. Okay, so what this means is that okay, so here let me also assume that the image of K is dense in the sense of minimax polynomials, or that gamma is smallest possible. Because otherwise you can add some elements of the integral 0 that are with no relation to the field. Okay, so this is a property that existentially closed fields have. And in other words, V of K star is dense in the kernel of the integral. Okay, so I want to take the statement and wonder a bit about it. So yeah, okay, so let's say that we are actually working with L1 of the space of norms, and let us define the adeles of K. So this is not perfect definition, but just for this kind of fun, as just sequences of elements indexed over all norms, maybe over equivalent norms, we take the same element, such that we have some condition. So usually the condition in adeles is that almost everywhere it's integral or 0, but here we just, okay, in this version, in this provisorial version, let's say that we just want the function to be L1. So that is defined by taking valuations at various places. Okay, so then gamma is GM of these adeles divided by GM of the integral adeles. So by this I mean adeles such that this function is non-negative. So if I take GM, this just means that norm of AV V is 1 almost everywhere for almost every V. Okay, but so here we see that GM of K is dense there. So hence, for existentially closed GVFs, the following double quotient naturally appears. We have GM of adeles, GM of integral adeles, and GM of K. And okay, this is just the kernel of the integral. Well, okay, it's not the kernel of the integral operator, but it's in the kernel of the integral operator. This is also in the kernel of the integral operator by definition. So we have the integral that we take a sequence and we just integrate this function, which is in L1, so we are happy. And now we know that this is dense in the kernel. So what this sort of says is that this is like an approximate isomorphism. But okay, but this is what? This is GM bundles, so just line bundles on K. Okay, and so this is variance uniformization. But okay, here I sort of defined the top, but I didn't say what are those. If I knew what are those, maybe I could do some higher GLN quotients. So let's try to do this. So, okay, so what would be the definition? So if V is a finite dimensional space, vector space over K, then U from V to gamma infinity is maybe adelic vector space. Yeah, if U of X is infinity, if and only if X is 0, U of lambda times X, where lambda is in K, this is V of lambda plus U of K X, and U of X plus Y is bigger or equal than minimum of U of X and U of Y plus minimum of V of 2 and 0. Okay, so yeah, okay, so the point is that if we have a function with integral 0 or some other function with integral non-zero, we can just like move the valuation by adding to everything this function, and it will satisfy these axioms. So, and this is maybe a higher dimensional definition that one could take. Yeah, I don't know if this is the perfect definition, but okay, it has been considered by Chen and Morivaki and by Beljakov in a similar language. Yeah, okay, so really the question I would like to understand is, can one describe existentially closed GVFs in terms of having not many adelic vector spaces, maybe finite dimensional space of invariance. Again, okay, this is maybe in quotation marks because like here, this is only dense, so this quotient maybe is not actually an isomorphism, but like approximately, this is and so maybe to just give you some examples where these structures naturally appear. So somehow, if I have maybe just example. If I have an arithmetic varieties with scheme over integers with a line bundle and H is a Hermitian metric, then I can consider the global sections of these line bundles, and I can also consider the rational sections. Okay, and then this is a finite dimensional vector space over Q, and this lattice, this integral lattice, gives you a family of norms over each places, and also the subnorm, the subnorm corresponding to the metric gives you an Archimedean metric over the Archimedean place, and so in fact this will be equipped with such a structure where one takes gamma to be L1 of primes and infinity. And this then translates to having a family of norms. So these structures appear in nature, and invariants of these structures are well studied, and you have Minkowski and so on and so on. So okay, let me finish just on this question and also on maybe a related question that, yeah, okay, so this is maybe some description of existentially closed GVFs, but like for example, in the Berkovich setting, you really can do geometry. You don't only have Berkovich analytifications, but you can glue them out of local pieces. And so the dream would be to do it here. So my way of trying to say something is to understanding first these existentially closed things, but yeah, I don't know. Okay. Thank you.
Are there any questions?
So, I mean, could you give more examples? Like, is there an example that you can write down of just like an algebraically closed GVF that is not existentially closed, for example?
Oh, yeah. So what you can do is, if you do this over function fields, then you get homomorphisms on Picard groups of varieties. So you can take a function field with two variables, and you can take, so it's P1 times P1, so you can take some unsymmetric divisor so that the height of S and height of T is different. And then you can take the fixed field of the involution exchanging S and T. And so then this has the symmetric Galois extension that I mentioned that it exists, and one can show that if you have an existentially closed GVF that is a symmetric Galois extension of some, then this GVF extension needs to be unique. But this one is not unique because you can take the algebraic closure of this, which as a field will be F, but it will be a different extension because heights of the variables are different.
Can you say something about how you solve how you show that Q now is closed? How you find the solutions?
Yeah, so this is actually related to this example. So the point is, I told you that the GVF structure is essentially a homomorphism from the space of adelic divisors, or like this Picard, this Pic hat. But if you have these conditions that we had at the beginning, we had only finitely many. So you start with some homomorphism, and you need to approximate this homomorphism on some finite dimensional space. And then this becomes some optimization problem. So you can cook up an energy functional on this finite dimensional piece of the space of adelic divisors, which are like maps to Pn. And then because the space is finite dimensional, you can solve the optimization problem by compactness of the unit sphere. It has a solution, and then so then what you end up having is on the variety defined by the equations, you have some special Hermitian line bundle, and then you have to use an arithmetic type of Bertini theorem that tells you that you can find generic sections of this line bundle which will cut out to some good point. But this is not only geometric Bertini, but you also need to control the norms with respect to different places of these sections. This is like a quick sketch.
Other questions? If not, let's take on.